Today to present DINOv2 in this coffee talk series that we have, in weekly basis. And the title is Learning Robust Visual Features Without Supervision. We'll actually find out what is it. But actually, I'm quite excited because, at least for my work here, I consider it as kind of my GPT, but for images. And we'll try to explore, what happened in this paper and what was the contribution. And in order to do that, I also want to recap a little bit on foundation models, a little bit as well on vision transformers, because this will be necessary to then understand DINOv2. And then we'll also discuss about some architectural applications, like how we can actually use this. So let's start by explaining a bit, what is the holy grail of foundation models. So ideally, what we like to have is a retrained model, which is general purpose in the sense that will work across different tasks and data distributions. So what that means is that imagine that we have this model that we have already pre-trained, maybe with a large data set, and we passed an image, and then we get feature vector. And then what we can do is, perform a certain number of downstream tasks. So this could be classification, instance retrieval, depth estimation, any task that comes to mind, and this will work. And on top of that, what I mean by data distributions is that if we plug images that were different from the curated or the data set that we came up with to train the model, this would still work. So that would be ideally what we want to have. And let's see, for example, that in this case, I want to show you that DINOv2 as motivation, for this talk, for a certain number of tasks, right? As you can see here, segmentation, classification, instance retrieval, as I mentioned before, it performs much or outperforms other methods, as you see here, both other self-supervised methods, so weakly supervised methods, especially when we scale up. So now the question, of course, is how we can actually achieve this. So this is what, they got there. The results are great, but how we can actually get this to work. And if we see here, I like to explain this today through the lens of the success triangle or triangle of success, which I slightly modified from the content that probably you can find very soon in Introduction to AI and Architectural Design that will be in EDX, where there actually you have these three components: compute, data, and algorithm. And once you have all those three, then you can actually have very successful working, maybe in this case, the foundation model. And my slight modification here is that I will introduce model in one of the vertices of the triangle, right? And I like also to motivate it through natural language processes, of course, like, GPT, everybody knows about that, and how that evolved very quickly and successfully over the past years. And in that case, we have this, architecture model that works rather well, the transformer. We, we have maybe, or OpenAI has the compute power to actually pre-train that model. And on top of that, we can get a lot of data from internet, right? So if we have these three components, we can make this work. Now let's see how we can apply these to images. So if we focus on the first component that I mentioned, the model or architecture, that would be the transformer, right? As I mentioned before in NLP. But when we go to vision, we can reuse some of the components, which I also recommend. I guess most of you are already familiar with attention is all you need. And I don't think we maybe need a session to explain that paper. But basically what we use is an encoder, which is based on the encoder-decoder version of that paper I mentioned just now. And then we apply this for images. How we do that? Well, if you have a sentence, so, for NLP, usually you would split this sentence into words or tokens, not exactly words, but pseudo words, right? In small tokens. And for images, what we do is we also split the images into patches. So here you see a certain number of patches, and then we can actually have then this sequence of patches, like if they were words within our image. So what we do is follow a very similar process. We compute embeddings for each of these patches. We also sum the position embedding, so where they are located within the image. And on top of that, I would like to highlight that we have also the CLS token, which is something that we add on top of all these patches that we have. And then when we pass this through our encoder, from which we will have this multi-head attention, but we compute the correlation. So how all patches with respect to all patches attend to. So which, where is paid attention within our patches of images. Then what is interesting is that we will get an output, but we'll get the output that comes from that CLS token, which actually attended to all the patches in the image. So as I said, I wouldn't like to go into detail about this, but what I like you to get from here is that we have a very successful architecture, like a transformer, that we reuse for image processing in this case, and then we split into patches. We compute embeddings. We add this CLS token. We pass it through the transformer encoder, and then we'll get the feature vector from this one that we can then reuse for downstream tasks, as I mentioned before. So having this in mind, you see we have already completed one of the 3 blocks of our triangle of success, but then we still have these 2, right? And especially for image with respect to text, it's a little bit complicated to get high quality or good data that we can use actually to pre-train it. And actually, I think that's one of the strengths of DINOv2. And so I took here the abstract from the paper and kind of highlighted with different colors what I think are the most important contributions. And with respect to data, you see that they actually came up with an automatic pipeline to actually build a diverse and dedicated curated image dataset. So this is one of the main contributions. Once we have that, then we can pre-train through self-supervised vision transformer that I just mentioned before. And then we can also distill it to smaller models as well. I will also explain that slightly later. But in general, you see that maybe they haven't focused so much on the architecture, but what they are actually providing is a way to come up with this data. And also, of course, is Meta. So this paper was released by Meta. So they have the compute to actually pre-train this huge model. So in general, if we take the VIT and then add these 2, we can already have the ingredients for success. Now, how we can actually come up with this curated image dataset? So what they actually did is to have first a curated set of datasets. So this will not be huge, will be, let's say, a small scale of, very already interesting and high quality, let's say, datasets. Some of them are listed here. I would like also to highlight that, Seran, that is here with us, is one of the co-authors of one of the datasets that were used for these curated datasets. And then on top of that, they also crawled many images from the web, which is around 1 billion images. Now, of course, these are not as high quality as the datasets that we already selected here. But then the game is that from this curated dataset, we'll use them in order to retrieve similar or similarly high quality or almost high quality data or images from this huge amount of images that we have there. And so in the end, what we will do is to come up with a data set that is comprised of a small set of these curated data set. And on top of that, some retrieved images that we got from this huge amount of images from the web. Now, how we do that? Well, I would like to explain briefly through some, diagrams, how we can approach it. So the first thing is that we want to get rid of duplicated images. So how we do that? Well, we first train a VIT, so a transformer, only on one data set. This is on ImageNet 22K. And then what we do is we pass those, images. We get the embeddings. And then what we do is to compute the cosine similarity. So basically, we find those that are very, very similar, right? And then we remove those. So we only stay with one of them. That's the first stage, because what we like to do is to remove, duplicated images. And in the second stage, we go to retrieval, which is what I mentioned earlier. And in this case, what we have is here, for instance, we have one image from this curated dataset. So this is a high quality image. And here we have this set of images coming from the web, right? This large scale dataset. And what we do now is to retrieve images that are close to that curated image that we have there. So we retrieve those. Now, there are two main approaches to do that, depending on the size of the query dataset. So if we have huge dataset, like in ImageNet, then in that case, what we do is to simply take the samples from, that are the nearest to that curated images that we have. So if we take, for example, 4 samples, so the 4 nearest samples from the web, then we are scaling up by 4 the size of our curated dataset. If we, otherwise we have a smaller query dataset, so in our curated dataset, the approach is then to perform k-means clustering. So we come up actually more clusters, but here you can see 4. And then what we do is we take the 10,000 nearest images from each of these clusters. So then we can actually scale up much more this dataset that we are coming up with. And so in the end, as I showed you before, if we follow through this clustering or sampling approach, we end up with around 142 million images in this dataset. So this was done through this automatic pipeline. And I think this is kind of inspiring also for, in the future, what we can do in order to not rely on these costly, high quality annotations. All right. And the second part I'd also like to touch upon is the self-supervised pre-training. So how they actually pre-train these transformers. And they follow this student-teacher approach, where you see here we take some global patches or global crops from the image for the teacher, whereas for the student we have maybe smaller ones, more localized ones. And then we pass them through the vision transformer. We get the embedding, we have a softmax, and then we get a kind of probabilities over those embeddings. And what we do is to compute actually the cross entropy between the teacher and the student. And once we get that loss, which is here, we backpropagate, so we train the student. And then you might think, well, they are kind of the same at the beginning, yes. But then what we do is that the teacher is actually, taken the parameters from the student following an exponential moving average. So it means it's not propagated or is not trained as the student, but is slowly picking up what the student is learning and is used a kind of, reference for the student to learn. So it's a self-supervised. And in this case, as we are passing, crops of the image, this is what is mentioned as an image level objective. But on top of that, there is another loss, which is is inspired by AiDAPT, which is another paper. And in this case, it's a patch level objective, which is a bit similar to what they do in NLP, in which from these patches, we mask some of them, right, for the student, whereas for the teacher has access to the full unmasked image. And now the game is different, is to actually, the approach I mentioned before is the same, but is to actually come up with what would be the class or the probabilities here for the tokens that were masked. So here, this will come up from the CLS token, as I mentioned before, but here is actually coming from those patches in the sequence of the image, right? And through these two losses and another bag of tricks that you can also check in the paper, then you can make this pre-training work very well. I would also like to briefly mention about model distillation because I found it very interesting. And that what it means is that when we train this, we use a large vision transformer. So it means we have many parameters there, right? But some people, even during inference, might like to use a smaller scale vision transformer. And you might think, well, we can train it from scratch. Yes, we can do exactly the same process with a smaller transformer. But what they actually show is that if we actually use the same approach, so we have a student and a teacher, and now we keep the teacher frozen, the teacher would be this, large vision transformer, and the student would be the smaller scale transformer, then we can use the same approach to distill or train a smaller transformer. And actually, what is very surprising is that, for instance, you see here that VITL, which is still large, relatively large, they compare it whether you train it from scratch or you train it through distillation. And what we can see is that through distillation, we get even better results. So yeah, here you can see some comparatives, and this is the effectiveness of knowledge distillation, right? So basically what they do is they train this the huge transformer, and then they distill smaller scale transformers that we can use. And I will show you later, now moving to the applications to kind of close the talk, how even for our case studies, we use the small one, so the smallest one of the vision transformers, which was actually distilled from this huge pre-trained one. So it's not actually pre-trained from scratch. So moving to the applications, I like to present two of them to close the talk. One is something that we are doing to predict the energy efficiency of buildings. And what we do is we take an aerial image of a building with a certain additional context on top of that. We pass it through DINO, and we get this feature vector, right? Which was what I explained you at the beginning. That was kind of what we like to do. But then the downstream task is a classification task where we have an additional MLP. And then we like to predict either the energy label or whether it's efficient or inefficient. So in this case, based on this aerial image, we like to know whether it's efficient or inefficient, or in some cases, we can even predict what would be the energy label. Second one that we actually implemented in a course that was taught recently in our department is actually to use aerial images and street view images, which are actually retrieved from publicly available data. So this case is in this case is coming from 3DBack, which is available throughout the Netherlands. And then by relying on DINOv2, we compute embeddings from both aerial images and street view images. We concatenate them, and then we can actually find similar buildings based on the distance of these embeddings that were computed, as I mentioned before. And then we can actually visualize this geographically. So this will be a second application. But of course, we can find many more, which was what I explained you before, right? That's the idea of foundation models, where we compute this general purpose. We have this general purpose model that come up with these features that then we can reuse for downstream tasks. Finally, I also like to add that while it's not, this transformer might not be the most interpretable model, we can still visualize attention masks. So this would be at the level of the multi-head attention, right? Where we have, which patch of the image attends to which other patch of the image. And we compute this attention score, so we can actually see where most of the weight is placed. And in this case, you see that, well, it found that there is a solar panel there, which might be a feature interesting in order to predict maybe the efficiency of that building. But I encourage you also to, do this qualitative interpretation yourself. So to close, some key takeaways. What we like to do is to come up with these general purpose pre-trained models that work, for many different tasks and for different data distributions. We actually kind of realize what could be the triangle of success to make this work. And what is especially, difficult for images is to come up with these curated data sets. If we pay attention to the model, then we can see that we can have or use this vision transformer, which is inspired by Attention All You Need, so the transformer paper, as many others. And then in order to resolve that problem with the data set, DINOv2 kind of performed this automated pipeline to come up with an augmented curated data set. And then a self-supervised pre-training, which of course you need, Meta's capabilities in order to train it. And then on top of that, you can also distill smaller models based on larger models that were pre-trained. And on top of that, we see that there is some flavor of many applications in architecture and some other fields, but that we can actually reuse what was presented here.